This is a quick introduction to fast Fourier transform. Let's consider the band-limited Fourier series representation of some signal f. This representation requires the values of a0, 1 up to an, and b1 up to bn. So there are 2n plus 1 unknowns, and if we sample f at 2n plus 1 points, we have a linear system in 2n plus 1 equations and 2n plus 1 unknowns. But it is actually possible to sample only at 2n points. So let capital N equal 2 times n, and the points we sample f at are xl, defined as t times l divided by 2n, where l ranges from 0 to capital N minus 1. Note that if we sample at these points, bn will not appear, because bn times sine of 2 pi n divided by t times xl is bn times sine of 2 pi n divided by t times tl divided by 2n, and that's bn times sine of pi l. And since l is an integer, sine of pi l is 0. Since bn does not appear, the unknowns are only a0 to an and b1 up to bn minus 1. And we end up with a linear system in capital N unknowns and capital N equations. Instead of working with this system, we pass over to the complex numbers. So remember that cosine x and sine x can be expressed in terms of e to the ix. There's a special value for x where e to the ix is equal to e to the negative ix, is when x equals 2 pi n l divided by capital N, where l is any integer. So cosine of 2 pi n l divided by capital N is simply e to the I 2 pi n l divided by capital N. And so the expression we have for fl can now be written in this form in terms of e to the I 2 pi k l divided by n. This comes from this because of this here. And as we can see, k can be integers -1 to -n minus 1, as well as 1 up to n minus 1. And that captures all the possible exponentials in both cos and sine at these angles. And when k is 0, e to the I 2 pi k l divided by n is 1. So the coefficient a0 divided by 2 is also captured in this summation as well. So that means fl can be written in this form. And now the xk's are the unknowns. One thing that we'll make use of is that e to the negative I 2 pi kl divided by capital N can be rewritten as e to the I 2 pi times quantity n minus k times l divided by capital N. And that's easy to see because anytime we add an integer multiple of 2 pi to the argument here, we don't change the complex number, and this is exactly what we have done. And now we're going to label x sub negative k as x sub n minus k, and we denote e to the I 2 pi divided by capital N by omega sub capital N. And with these pieces of notation, this product here can be rewritten as this. And so if we go back to the expression for FL, which is here, we can replace these with the omega notation. And now this summation is broken down into two. One part is from 0 all the way to n minus 1. The other one is from 1 to n minus 1, and the indices are negated. And we now notice that this is what we had before. So we're going to rewrite that as this. So this is now this. And we notice that as k ranges from 1 to n minus 1 here. These indices range from capital N minus 1 down to capital N minus the quantity of n minus 1. And since capital N is 2n, we can start from k equal n plus 1 up to capital N minus 1. And now we can put all these together. We have 0 to n minus 1, and then k equal to n here, and k from n plus 1 to capital N minus 1. And so the whole thing can be written as this. So FL is now conveniently written as the summation as k ranges from 0 to capital N minus 1 of some unknown xk times omega sub capital N to the power k times L. And this gives us a system of capital N equations in capital N unknowns x0 up to x capital N minus 1. And this system is over the complex numbers. Let's look at a couple of illustrative examples. When capital N is 2, that means lowercase n is 1. Omega sub 2 is simply minus 1. And the system is simply the matrix 1, 1 in the first row, 1 minus 1 in the second row, times x0, x1 equals f0, f1. And since we're interested in knowing the values of x0 and x1, we can solve this. But this has a closed form. x0, x1 is given by 1/2 times the matrix 1, 1 in the first row, 1, negative 1 in the second row, times f0, f1. When capital N is 4, omega sub n is equal to I, and the system looks like this. Again, this has a closed form solution. We can immediately write down the inverse of the coefficient matrix, and the answer is shown here. So in general, this is always possible. So for general n, whether or not n is even, the system up here has closed form solution that looks like this. So these are the function values of the function at the sampled points. And we can obtain these values by just performing a matrix multiplication. But that itself is actually rather slow, even though it's faster than solving the system up here, which requires order n cube operations. So to perform the multiplication here, the total number of operations is quadratic in n. For large n, for example, for compactest audio, 44,100, there is way too many computations. So in 1965, Cooley and Tukey gave an algorithm that has time complexity order n log n. And here is a sketch of their approach. So let's define this matrix Fn, and remember that this matrix appears in the closed form solution, but without the 1 over capital N factor in front. If capital N happens to be even, we can define this matrix omega n to be this diagonal matrix. And the result is that to compute this, you can first compute this, which is like this, but with the dimensions halved, as well as this. Again, something that looks like this, with dimensions halved, multiplied by this simple matrix here. So from this identity, if n is again even, we can continue this splitting idea with this and this. And if capital N is a power of 2, the splitting can continue until we're down to capital N equal to 2. And if you perform the analysis, the number of computations required will be order n log n, where logarithm is taken base 2. So here's an example. So suppose that the vector x is 1, 2, 3, 4, and we want to compute f4 times x. And we know that the closed form solution is given by 1/4 times this matrix here times x. So this is our answer. Now let's check it against the results given by the theorem. So f2x prime is 4, negative 2, because f2 is 1, 1, 1, negative 1. And f2x prime prime is 6, negative 2. So remember that x prime is formed from taking 1 and 3, and x prime prime is formed from taking 2 and 4. And now this matrix here is this. So we'll put these all together and perform the computations. We end up with the same thing as we have up here.